Hey everybody, welcome back to school. I know it's kind of crazy time for all of us, and I'm trying to go through and learn how all these new technology to me works. So bear with me as we go through it. I'm going to go through the notes for 3.1 and 3.2 today. And if you remember where we left off, 3.5, 6, and 7, we were factoring, dividing, and factoring sums and differences of cubes. Now what we're going to do is we're going to go back, we're going to go over the characteristics of polynomials so we can eventually graph these things. So first things first, right off the bat, it says we're looking at one variable polynomial, so we're only going to have x's, or any letter, but for this case we're going to be using x's as our variables. And what a polynomial is just a long list of terms, all separated by addition and subtraction. And each term that we have is going to have a coefficient out front. So that's like the a values that are there, a to the power n, an minus 1, and so on. That'll be any real number that could exist. So it could be fractions, root numbers. And it's combined with a variable. And that variable, in our case, we said it's going to be x. And each of the exponents that we have in those variables, in order for it to be a polynomial, needs to be a whole number. We're not going to have fractions. We're not going to have decimals as our exponents. And that's kind of what it says down below. In terms of what polynomials may look like, we see the ones over here on the left where each of them has coefficients that could be whole numbers, like the first example here. We see ones that could have fractions in them. We see ones that could have roots or things that would be decimals in them as well. So that's okay for them to be polynomials. But one of the main things is that the exponents are always going to be whole numbers, and they're going to be positive whole numbers. So if you look down the entire list, we see that each term has a positive whole number as the exponent. For the ones that are not polynomials, you'll see that these would result in either an exponent that is not a whole number or an exponent that's negative. So like the first one here is not a polynomial because we see a root. We know a root has an exponent of half. The second one's not because the bottom here, 2x, when we have an x value on the bottom of a fraction, part of the denominator, we know that that's going to have a negative exponent. Third one here, we see that has a -1. For the next one, we see we have a rational function here, and a rational function is not a polynomial. It may be able to be simplified to a polynomial if you divided them, but this one couldn't. What would exist is a horizontal asymptote would exist in this equation, so we wouldn't be able to do that. For the sign's not in the form that we saw above. It's not in the form of a number, a variable, being added and subtracted to other numbers and variables. And finally, the last one down at the bottom here, we have x has an exponent of 2.5. We know that for polynomial, exponents won't have decimal numbers. So as we continue through, we have some key terminology that's important in this section. So things that are important to us are going to be degree. We've talked about that back in grade 10 and grade 11. Basically, it's the biggest exponent that exists. So if I look at all four terms here, I see that this term at the beginning has the biggest exponent. It's 3, so therefore the degree of this polynomial is 3. In terms of the leading coefficient, leading just means first coefficient. So that just means if we look at a polynomial, we find the highest degree term, and the leading coefficient is the number that's in front of that. So in this case, it would be the 7 would be the leading coefficient of that polynomial, because we have that x to the power of 3, which is the highest degree of all those terms, and the coefficient on that highest degree term is 7. Next, we talk about turning points. So now polynomials can look very different, and any turning point is a point where we go from either a positive slope to a negative slope or rate of change. So for example, if I have some graph, let me get some colors here, that looks maybe like this. This would have two turning points. It would have one at the top here, and it would have one at the bottom here, because we're going from a positive rate of change to a negative rate of change. It has a turning point down at the bottom. It's going from a negative rate of change to a positive rate of change. So any spots that it turns would be considered a turning point. And these would be considered local maximum and minimum. So for the one that we have over here on the left, let me you go back here. This would be considered a local maximum because it may not be the maximum for the entire function. I know that it's not the maximum for the entire function because the arrow over here on the left tells me that it can, or over here on the right tells me that it continues up forever, which means that its actual maximum would be infinity. But this spot that we have over here on the right would be considered a local maximum because within its region that it exists, it's the highest spot that exists within that region. It's any spot that would go from a positive slope to a negative slope. So you can have multiple local maximum or minimum. So like for example, if I drew one here and I had a graph that looks something like this, so maybe here, here, and it continued up forever like so, we would know that there would be two local maximums, one here and one here. It's not the maximum of the entire function because that arrow over there on the right tells me it continues up forever. But they would be local maximums because we're changing our slope from positive to negative. We also have local minimums. Those would be just the opposite, where the bottom of the graph. So for example here, we would have a local minimum here and a local minimum here because that's where our slope is changing from negative to positive and changing from negative to positive. So it's just the opposite. Any function can have n minus 1 turning points, where n is the degree. So for example, for the ones that we have above, we see that we have polynomials with degree of 3. It could potentially have 2 turning points for each of those ones. If we had a degree of 10, we could potentially have 9 turning points. It doesn't mean there has to be 9 turning points, but there could potentially be up to 9 turning points. And another one would be like a quadratic, for example. We know a quadratic has a degree of 2, and we know that a quadratic is a parabola and it has 1 turning point, as you can imagine here. If I was to draw out a quadratic, doesn't matter what they look like, we know that the degree of quadratics is always going to be 2, and there's only going to be 1 turning point because I see that one down at the bottom, right there at the vertex. Other things that'll be important to us in terms of terminology, we have our zeros. Let me take these off. So zeros are the same as it was back in grade 10 and grade 11. Zeros are the points where the graph crosses the x-axis, the x-intercepts. Graph can have the same number of degree, n, number of zeros. So a quadratic has degree of 2. It sometimes could have up to 2 x-intercepts. So if I draw it on here, so once again degree is 2 and we have an x-intercept here and an x-intercept here. It can have up to 2. Does it have to have 2? No, it could have 2, 1, or 0, and we know that from our work back in grade 10. So you can have up to as many x-intercepts as there is in the degree. And finally, the last one that's important to us here is the end behavior. End behavior is just what happens on the very far left or very far right of the graph. Where is it going? All right, let's look at some examples here. So example 1 says, state the leading coefficient in the degree and the maximum number of zeros and potential turning points that the graph could have. So for these, all this information is going to come from the term that has the highest degree. So for the first one that we have here, we see that this term has a degree of 4. The others have a degree of 3, 1, and the constant has a degree of 0. So that term that's underlined is the term in the polynomial that has the highest degree. So all the information is going to come from that. The leading coefficient is the number in front of the variable. That's -8. The degree in this case is the exponent of that. It's 4. The possible number of zeros that we have, well, we know that we can have the same number of zeros or x-intercepts as there is the degree, in this case 4. And the number of turning points that we can have, well, I can have 1 less than the degree. So in this case the degree is 4. I'm going to subtract 1 from that. I know that this graph could potentially have 3 turning points. Same goes for the second one that we have here. This one is not in descending order of degree. I have to search. The first term has a degree of 3. Second term has a degree of 1. Third term has a degree of 4. Next has 2 and 0. So I know that x to the power of 4 is the degree that is the highest. So I'm just going to go through these. Leading coefficient. Well, in front of there's no number, but I see plus, which means positive 1. The degree of that term is 4. That's the exponent. Number of possible turning points. It's the same as degree, which is 4. Possible number of zeros is 4. And the number of turning points is 1 less than that. We have 3. And finally, for the last one that we have over here, I see degrees of 3, 5, and 7. 7 is the highest of all those numbers. So the leading coefficient is the coefficient on that number, which is negative 4.1. The degree is the exponent, which is 7. The possible number of zeros, 7. And number of turning points, 1 less than that, which is 6. So we get all this information. This is going to give us some important information about what the graph looks like. So what we have down below are what some graphs could look like with the equations down below. So if we look at the first one that we have here, I see that we have a degree of 2, and it's just a quadratic. It has one turning point down at the bottom. It has 2 x-intercepts right here, which is the same as the number of degree. Continue across, I see we have a degree of 4 in this case. So that means there's a maximum number of 4 x-intercepts. In this case, there happens to be none. Right? We could have up to 4 when the degree is 4, but in this case, we don't have any. Just like a quadratic doesn't have to have any. Number of turning points, I could have up to 3. In this case, this graph does have 3. It has 1 down here, has 1 up top, and 1 down below. So they would have 2 local minimums and 1 local maximum in this case. Continuing through, we see we have a degree of 3. So that means there could be up to 3 x-intercepts in this case. In this case, we do have the 3. We have 1 here, we have 1 here, and 1 here. We also know there could be 2 turning points. In this case, there are 2 turning points. There's 1 at the top and 1 down at the bottom. Oops. As I continue through, we see that the next one we have a degree of 4. So that means there could be 4 x-intercepts. We have 1, 2, 3, and 4. We know there could be 3 turning points. 1 less, 1, 2, and 3. And continue through, same idea. Degree of 6. There could be 6 x-intercepts. In this case, we only have 2 of them. 1 here and 1 here. We could have 5 turning points, 1 less. We have 1, 2, 3, 4, and 5. And lastly, we have a degree of 5, which means we could have 5 x-intercepts. 1, 2, if I could work, 2, 3, 4, and 5. And since the degree is 5, we could have 4 turning points. We have 1, 2, 3, and 4. All right, so lastly, we're going to try to bring all these together. One other thing that we're going to kind of touch on a little bit is what do the general shape of functions look like? So really there's 2 general types of shapes that our polynomial functions will look like. What we're going to do is I'm going to go over to Desmos and show you the graphs, and we'll try to see if we can determine any characteristics that are the same. So what I'm going to do first, I'm going to put in y is equal to x squared. I'm going to put in y is equal to x to the power of 3. Y is equal to x to the power of 4. So if I look at the ones that are even, y is equal to x to the power of 2 and y is equal to x to the power of 4, you might notice a couple things that are the same. I'll only put those 2 on here. It's that they both have the same end behavior. They both start and end on the same side, up at the top. For the cubic function, and I'll put it up, its end behavior is opposite. One starts at the bottom and ends at the top. And that's going to be true of all odd functions. So if I add things like y is equal to x to the power of 5, or I change that to 7, or I change that to 9, or I change that to 11, you see that the end behavior is on opposite sides for odd degree functions. One thing that you might notice as I zoom in here is that the higher the degree gets, the flatter our graph gets around the origin. And then it takes off as x gets bigger quite a bit faster than the original x to the power of 3, than a degree that's lower. That's true for even functions as well. So if I put on y is equal to x squared, and I put y is equal to x4, take these ones out, and I put in x to the power of 6. Sorry, let me just back up here. Power of 6, see it's flatter around the origin. 8, even flatter. 10, flatter. Can even put in numbers like 100, very flat. 1000 is an even number, very flat. And you see that around the origin it gets very flat. However, as x gets bigger, it takes off quite a bit faster. Probably not going to be dealing with ones that are 100 and 1000, but the idea is that it's an even number, like 16. It's flatter around the origin, but takes off a lot faster as it gets x gets larger or smaller. So we're going to be using that idea in our notes. I'm going to go back to graph what we've got. So I know that the even ones, the x to the power of 2 and x to the power of 4, generally look the same. It's just the one with the higher, whoops. Let me redo that one. The one with the higher degree is a lot flatter around the origin. So it looks something like that. Whereas a cubic function is going to have end behavior at opposite sides. And the higher degree will be flatter around the origin as well. So this one here might look something like this. And x to the power of 5 might come up but be flatter around the origin. Take off. So the description of the graphs of our even functions would be a U-shape. For the odd functions, they're more like a twist. All polynomial functions, no matter what, have no asymptotes. So that's the general shape of what the graphs look like. The only other thing that we're going to look at is what happens when we have a negative leading coefficient. So one thing I know about quadratics is when they have a negative leading coefficient, basically our graph is flipped over the y-axis and it would end up looking something like this. If we had a negative leading coefficient for a cubic function, same's going to happen. It's just going to be reflected. Instead of starting at the bottom and going to the top, it'll end up looking something like this. For a quartic function, same idea. It's going to be flatter around the origin, but it's just going to be facing down. Notice the end behavior for the even functions are on the same side. The end behavior for the odd functions are on opposite sides. And finally, you can imagine the last one would, instead of starting at the bottom, start at the top. Be flat around the origin and end at the other side. Just reflected over the x-axis. So let's go down and answer some questions. We're not going to be graphing them, but we're going to be answering some questions about these. So down below, it just reiterates what we just said. The basic shape of a polynomial graph is determined by the degree. If it's an even degree, well, it's a U shape. And if it's an odd degree, we have a twist. You write that down below. Even degree, a U shape, and behavior on the same sides. Odd degree, a twist shape, and behavior on opposite sides. The higher the degree is, the flatter the graph is around the vertex or the origin. For leading coefficients, we talked about this a little bit. It says positive leading coefficients and behavior had the same as the parent function. So x to the power of 4 had the same behavior as x squared. Both started at the top and ended at the top. For a negative leading coefficient, it's just the reflection of those. So imagine flipping a quadratic over the x-axis, so it's facing down. Well, x to the power of 4 would also have that same behavior, both on the bottom, as we kind of showed. Whoops, up above here. So that only difference is that leading coefficient, if it's negative, it reflects it. Doesn't matter what happened on any of the other coefficients of any other terms in the polynomial. It's just that one that we have that leads our polynomial. So we have a couple of polynomials here that we just want to answer the characteristics for. So example 2 says, describe the degree, leading coefficient, and then end behavior if we know that, as well as the number of possible turning points, number of zeros, and any y-intercept of each polynomial function. We can find the y-intercept by just substituting in x is equal to 0. It's always an easy one to substitute in. So for these polynomials that we have above, the degree is the highest exponent. So for the first one that we have over here on the left, we have 6. For the one over here on the right, the highest exponent that we have is 5. So one is even and one's odd. So I know that the one on the left will have end behavior on the same side, and the one on the right is going to have end behavior on opposite sides. The leading coefficient is the number that's in front of that term that has the highest degree. So in this case, our leading coefficient is 5. That's positive. For the one over here, I see that my leading coefficient is -4. It's negative, so I know this can be reflected. In terms of end behavior, we know that since we have an even degree, we're going to have end behavior on the same side. For the one over here on the right, I see we have a degree of 4, so I know the end behavior is going to be on opposites. That's what we're most interested in right now. Once we start sketching, we'll say, well, is it opposite going from top to bottom, or is it opposite going from the bottom to the top? Possible number of turning points. Well, we know that that's n minus 1 of the degree, which in this case is 5. For the one on the right, the degree was 5, so we have n minus 1, which is 4. So it could have 4 turning points. Possible number of zeros is the exact same as the degree, so it could have 6 x-intercepts. This one could have 5 x-intercepts. The y-intercept, I get that by substituting in x is equal to 0. And since each term has an x, I know it's going to make each term 0, so I know that the y-intercept is 0. So it's going to be at the origin. Same goes for the one over here on the right. Each term has an x in it, so if I substitute in 0 for x, each term is going to become 0. And finally, shape of the graph. So I want to know, is it a U-shape or is it a twist? The one over here on the left is an even function, so it's going to be a U-shape. And the one over here on the right is going to be a twist. We'll get into sketching them later on. It's just a matter of getting these characteristics down first and going through them. So what you can do is you can pause if you want and try this one that we have down at the bottom to see if you can figure out what the degree is, leading coefficient, and so on. This would be an example of one that we should be able to come up with. So if you want, pause it, but I'll continue through and I'll go through it. So I need to find the highest degree. That's the first term that we have in this case, which has a degree of 5. So I know my graph is going to be a twist. My leading coefficient is a -3, so I know it's going to be reflected. My end behavior will be opposite sides then. Possible number of turning points is 1 less than the degree, so in this case it's going to be 4. Possible number of x-intercepts, 5. Notice it says possible, doesn't mean it has to be 5. It says it could have a maximum of 5. My y-intercept, so if I plug in 0 for x into each one of those terms, the only one that doesn't have an x is that -5 on the very end. That's the only term that won't become 0 when I substitute in x as 0. So that means that's going to be the only number that remains. And finally, the shape of the graph, we have an odd degree, so it's going to be a twist. So what we're eventually going to get to is we're going to start with these graphs. We're going to say, okay, well, how do I graph these things? Well, what we know from this section is that we have a leading coefficient that's negative, and we have an odd degree. So now normally an odd degree function looks something like this. However, we have a negative leading coefficient, which means it's going to be reflected. So instead of starting from the bottom and going to the top, it's going to be the opposite. We're going to start from the top and end up going to the bottom. So it's going to look something like this. That's all that we know about the end behavior. We're going to get into things like, how do I find out the number of, or where the turning points would be, where the x-intercepts would be. In order to get those x-intercepts to zeros, I'd have to factor that equation up at the top. I would plot those points on the graph. So really, at the end of the day, this graph that I have over here on the right, the only thing that we really know from the characteristics that we went through today are that it begins here and ends here. In between, we don't know much about it yet. Might, could look something like this. I don't know, something like that. But for now, we just know that the end behaviors are either on the same side or opposite sides. And we also know that our degree will tell us the shape of the graph and our leading coefficient, whether it's been reflected or not. And that's about it for this section. In the notes, I talked about where you can get your textbook. So these are the questions